Welcome to another fireside chat with the experts. Today, I'm really happy to have uh, Jonathan Jimenez, or JJ, like we call him, our VP of Software Development, hosting the chat. And the presentation today is how AI is changing the way we make and inspect things. JJ has a unique perspective as a software engineer and with a lot of experience developing AI and machine learning engines for X-ray applications. So with that, take it away, JJ.
Yep, thanks, Phil, for the introduction. Like Bill said, today we're going to be doing how AI is changing things. And for this presentation, because a lot of the people tuning in are going to be from SMT, we're going to use SMT as an example, but the takeaways are much broader than that, and you can see how your particular industry would fit in. There's contact details on the screen there in case you guys need to get a hold of us, and at the end they'll be available again. So basically what this presentation is going to be is a broad overview of the process. So we're not going to get down to the exact math, but we're also not going to skip over some important details. So we're going to talk about the actual process to develop a system. And again, this is going to be for an SMT. What is the big goal here? So the idea is you may have, systems in your factories or in your process that give you data. And for a long time, that was what everybody wanted. They wanted data. And what we're seeing now is that what's most important is being able to take that data, convert it into useful information, something that can be acted upon, and take action on that. And so the idea is that the users will be able to basically elevate what they're working on from, lower level work, gathering data or looking at data, to using the information to take action. And then a little bit later, we're going to move on from there. Like it says here, this is the beautiful X-ray image. We can learn a lot from there, but the idea is we don't need to look at them anymore. We want to get past that. So this is what a typical SMT line. This is what a typical SMT line looks like today. So you see, a printer, and then we have our solder paste inspection, our pick and place. We go to reflow, and then we go to inspection afterwards, whether that be optical, X-ray, or both. And so, to understand how we're going to gather the data and then formulate action from it, we have to understand what data is available on an SMT line. So the first machine that's going to give you real data in a system like this is going to be the solder paste inspection. So that's going to tell us things like excess solder, solder bridges, or insufficient solder. Again, this is data that you as a operator or as a engineer may already have from your machine. And the idea is that we're going to take these items from each of these individual systems, and then we're going to be able to put it together. So your SPI machine may know the excess solder, solder bridges, and insufficient solder condition of the board. And so then the next system is the pick and place. The pick and place is going to introduce issues. So for example, just like the solder paste process introduced excess solder, we can have a misalignment, an issue with polarity, or an issue with a missing component in the pick and place. Then we move on to the reflow oven. The reflow oven can introduce, through misuse or issues with supplies, it can introduce voiding, bridging, solder balls, excess solder, insufficient solder. To go over a couple of these issues, for those of you that may be in a different industry and you kind of want to understand where we're getting this data from, most of the issues that happen here, with the exception of the ones that happen in the pick and place. So that includes the excess solder, solder bridges, insufficient solder, and from the reflow oven, the voiding, bridging, solder ball problems, excess solder, and insufficient solder again. All these issues are going to stem from issues with the SMD solder. And so this is a paste that comes to the factory and it's placed into the solder printer. or the solder paste machine. And all these issues are going to be either problems with the design of the board where the stencil for the board is incorrect, or the solder itself is a problem, or the process, for example, in the reflow oven, it's going through too fast or too slow. But most of these issues are dealing with the same part of the process, right? They're all dealing with the solder. The pick and place is a little bit different, but it can also affect those solder related problems. And so then as we move on, we get to the inspection area, and this is where it's important to gather the data. So from the inspection area, whether that be AOI, AXI, or preferably both, you can get information and statistics and do statistical process control based on the results of the data you're getting from the AOI and AXI. But these results are going to be down to the machine. So traditionally, you have your AOI results separate from your AXI results, separate from your solder paste inspection, and separate from any information that might be available to, for example, the pick and place. So the idea here is that we can take the measurement data and figure out not only is it acceptable at this moment, but what's the trend? Is it getting better? Is it getting worse? And again, this is available from reasonably new AOI, AXI machines. If yours doesn't have it, then that's a problem. But this is what we have right now. And so the idea is, okay, well, how do we process this information at the moment? So currently, a line manager is going to start at the beginning of the line and do his rounds up and down, up and down. And the idea is that they're going to be checking the information from each individual machine, and then they're going to be analyzing that data and deciding is everything okay? Is there an issue? What could be causing it? If you have a very good line manager, then this probably works most of the time. This line manager needs to be incredibly experienced because they're operating or they're managing a large number of machines. They're all doing their own thing. They're all producing their own data. And so if you're lucky, if you have a very experienced line manager, it's working at the moment. So the problem is that, as I said, you require a very experienced line manager to be able to do something like this. You can have issues where the operator of an individual machine doesn't catch the problem, doesn't flag the line manager. That's a problem that's going to happen through training or through when an operator is doing a repetitive task. It's easy to forget what they're working on or let details slide. But even if the operator catches it, the next problem is, well, can the line manager take all these reports that are coming from the individual machine operators, put that together and understand what the problem is? And so again, you need a high level of experience for your line manager to be able to do that. So what is the idea here? The idea here is to take the role of the line manager and help him or her, and get the information gathering, the data gathering, and the creation of information, and automate that part so that the line manager can take information and then act on it without having to manually go through and grab all that information himself, all that data. So the way we do this, the purpose of this talk, the trends that we're going to in the industry and other industries as well, is the idea of data fusion. So here we have kind of a system, right? So we have data entering a function, and the function is going to put together the data that is coming in and then give a result. And so you have information here. The example is AOI, SPI, AXI. Other SMD lines are going to be more complicated than that. Other industries are going to have different sets of data, but usually it'll be something similar, where there's some sort of optical inspection or X-ray. Medical will have this. You can fit the data that you're putting on the left there to whatever your industry might be, but the general ideas are going to be the same here. So you have the information coming in from the different systems, and then this is obviously a simplification. This middle step here, where we have these different values of statistics and information, this is actually already an important step which is, do you have the ability to represent that data in a way that you can operate it like a function? And so then we take the fusion system, which takes all this information, and then we can get a result from that. And from that resulting information, you can make a decision, take action. So what lets us do this? So everybody's heard about big data, and for years there was big data before there was AI. And AI is the problem, the solution to the problem that is big data. And big data is the solution to the problem, which is what's happening in our process, right? So you can't have one without the other. It doesn't help if you have gigabytes and gigabytes of data if you don't know what to do with it. And so what's allowed us to make systems that take this information in and make produce information and take actions on it is low cost GPUs and advancements in machine learning. And so the idea is we can build a system, have lots of compute power that can take in all this information that I showed you on the previous slide, and then it could pull meaning from it. So for example, understand how the data is connected from one machine to the other, how the data is connected from, in the time series. So how it's connected, the data from an hour ago is connected to the data from now, the data that's coming out now. And then the idea is we're not just looking at one piece of data and then another separately. We're taking all the data in and we're making decisions based on all of it at the same time. So for example, if you have a solder paste inspection and it has an egregious failure, sure, you fail it, you do that now. If it looks great, you pass it, you do that now. What you don't do is, if the solder paste inspection results in a marginal result and the AOI for that same area results in a marginal result and the AXI results in a marginal result, you are currently not, or at least most customers do not have a system whereby they can see, okay, there is actually something wrong here. We're not finding it. It's not a usual failure that our machines can catch easily, but they're detecting the side effects. And so what we can do is take advantage of the fact that together that information is more valuable to figure out what is happening, underneath, what is actually causing these differences in results. And again, for a BGA, let's talk about how this might work. So the AXI can automatically identify a bad BGA, for example, if it's listed egregiously. But if we take the AXI and the SPI and the AOI data together, we can get a much better understanding of what is happening to that BGA. So for example, from the AXI, we might see that there's a short, and the SPI says that there was slightly too much solder, and the AOI can see that it's lifted. So now we know, there's probably an area that has excess solder. Now that sounds like something we can do now, but the next big step is taking all that information for every component the entire time, and then over data from earlier in the day to later in the day, and putting that together to figure out exactly what the problem is going to be, or where is it heading. So you may have this BGA that failed, but you're going to start seeing components nearby fail because these issues are going to start manifesting themselves more aggressively as the process gets worse, and then it's going to cause more errors. The idea here is to find them before they happen. So we take the extensive data set of all the issues. We have partnerships with SPI and AOI companies, and we can take care of the AXI information and data and gathering and analysis. And so together we can understand where the trend is going and the data. And so here's an example. It kind of shows what conceptually is going on. This only shows 3 degrees of freedom, three dimensions. And so here we have boiled down the process of making a PCB assembly to 3 things: solder paste, the actual solder paste quality, the printer, and the oven. And obviously there's a lot more to this, but this gives it, boiling it down to 3 variables makes it a lot harder to see. So you can see that for this one, our system has determined that the solder paste is doing really well at this time. The printer has a few minor issues, but the oven is causing problems. The oven is causing defects in the samples. And so this is what it might look like if we were only looking at 3 degrees. If we move over, you can see what it might look like over. So we can see what this might look like when we add time. So instead of making it a spatial dimension, instead of adding an arrow here, we're splitting it up over 3 different times, so you can kind of see how it's changing. So you see, if you look closely, you'll notice that the printer does not change at all. So the printer stays in the same position. We don't expect it to change too much, but we're not having any more issues, right? So it wasn't doing great in the morning, but it's keeping steady. The oven is the same. So it was, it could have been a lot better. If this system were run like this, it's because the operators or the line manager decided that this is acceptable for the board that they were building. But you'll notice the important part here that the solder paste is getting worse. And so something is happening from 8 to 10. So it could be that they opened up a fresh bucket of solder in the morning and it's just drying out. It's getting worse and worse throughout the day. It could be that, their air conditioning broke and the humidity conditions aren't being kept. So it can be a lot of different things, but the idea is that we figured out that the solder itself is the problem here. It's not the oven, it's not the printer. The solder is getting worse as time goes on, and we can detect that. We can, let the line manager know, hey, something's wrong. We're not storing the solder correctly. It's getting worse. All right, and then we have this information, we have the system, we understand what we can do with it, but what is that going to look like for an actual process? What is that going to look like for taking this information and making something of it? So you can imagine that at first, we're just going to have reports to the line operator. And this is something that is a lot closer to kind of like an assistance role. And so the idea, this is what I had spoken about at first, is we take the load of analyzing all the data off of the line manager, and we allow the line manager to manage the line. We allow them to make decisions about what needs to happen based on the information that we've given them. But what they don't have to do, they don't have to run from machine to machine to try and figure out what each of them is saying. At this point, they have this information. They know that the solder paste is drying out. They know that they now need to figure out, first of all, grab another bucket of solder paste and switch it out. And now they can focus, the next 20 minutes on figuring out, hey, what's going on with our solder paste? Why is it drying out so quickly? Are we not putting the lid back on? What's happening here? The next stage is going to be a self-healing line. And so the idea here is if we can detect that, for example, the refill oven is going too slow, right? So spending too much time at each stage, then we can talk back to the refill oven and say, hey, speed up a tiny bit. We're having these issues. And obviously this would all be logged. A lot of times, in between stage, we're going to be able to recommend this and then have a line manager sign off on it. But then that way they can just make the decision. And then at some point, we want to get to the point where this is all happening automatically. So we're sending that information back and the machines are responding to it. And this doesn't go one way, it can go both ways. From the right side of the line to the left side of the line, or from the left to the right. So it could be that the solder paste inspection says, oh, this area here, it's passing, it's good, but X-ray, can you just make sure that you double check it? Or AOI, can you make sure you double check that area, just because there is a small deviation. We want, we need to gather more data about whether or not this is going to be an issue. And so you have the line talking back and forth to the point where you can get it, to minimize the error. And again, this goes back to that minimization problem, trying to take all these inputs and get them to zero, get all the issues in the different dimensions down to zero. So there's no reason why we have to stop at 3, and the systems that we have don't all look at 3. Here you see we added a fourth spatial dimension. So we had the solder in the printer, but now we're looking at the inventory. So we can do things like, using an integrated parts counter system. You can go ahead and see, hey, is there something wrong with these parts that are coming from the manufacturer? Are we seeing discrepancies when we X-ray those? Or if we have it in the inventory system, what solder paste is being used for a system, and we can detect, hey, this solder paste from this manufacturer is consistently giving us worse results than these other ones, because we've been tracking it down to which materials were used during a process. Then we know what we want to buy, who we want to buy it from, and how to, over the course of weeks, days, months, make the process better. So again, right now we get data over the course of hours, and decisions are made, over the course of hours. With data fusion, we want to make decisions over the course of, the line speed. And then the idea is we can also take those decisions, months-long decisions about like switching suppliers, and we can get information within days to say, yeah, this is a clear win here. So it's all about taking the information and changing the scope. And again, so what's the point? One thing is to speed up. Another thing is to have a higher level understanding of our processes. So you see on the right here, this is assembly. And so, in the past, we used a lot of assembly. If you use assembly nowadays, and that means, you're doing some really low level stuff, most software engineers won't be doing that. And so the idea is, as the, software engineering has gone up and up and up in abstraction, we've gone past actually wiring things up to assembly, up to C-level languages, and we worked our way up to artificial intelligence, where we have a much broader handling of the issues, where we give it the data with the expected results, and then we try and build a system that we don't really care too much about exactly how it works, as long as it understands what's going on and it can give us results. Just like that, we want to move our smart factories up. So we've gone from hand assembling everything to machines doing it, and as we work our way up, we want to have that just like we are automating the process of building the products. We want to be able to automate the understanding and the data gathering from that whole process. So and that's how AI is now, but that is what data fusion is going to be for the smart factory, right? So this is what's going to combine all that data and give us the gains that we got through automation in our understanding of the process. And yeah, so that is an overview of what a system looks like and what we've deployed. And I think right now would be a good time for questions if anybody has any.
Yeah, I have a question here, JJ, from Scott, and he is asking about. Sorry about that. So he's asking about digital twins, right? So he's asking about how do you see the ability of EMS managers to abstract manufacturing once these new techniques are implemented, and how is it going to enable digital? So digital twin is the ability to create a fully digital representation of the manufacturing line, the one that you showed earlier in the first slide, the ability to replicate that whole line as a digital entity. So you can literally copy and paste and have the same manufacturing line in Fremont, California, San Diego, or Hong Kong, right? So how do you see that enabling this abstraction of manufacturing going forward?
Yeah, that is right. I mean, you set that up beautifully. So the idea is that if we have a very sound understanding of the system, we know how it connects, we know which inputs cause which outputs, and we know the exact settings that everything has to have, and we have all the underlying information gathering built in, then that allows, for example, an operator to switch from one factory to another. So let's say one factory has one set of machines, another one has a different set of machines. The machines do roughly the same thing. It might be from a different manufacturer, but if they are set up with the same data fusion system, then they're going to have that same dashboard, and they can get the same information, the same understanding of the process that they would have gotten at factory A, at factory B. And to them, they are just looking at the overall process, right? So they don't have to go through the trouble of figuring out where does the solder paste inspection machine at factory A has this piece of data in this location, but now I'm at factory B and I need to figure out, oh, this is a different manufacturer, and I really just need to know this information because I have to make a decision, but now I need to call tech support or somebody who might be at that factory permanently to get that information. We don't need to do it. We don't have to worry about that. At this point, at this level of abstraction, because we're understanding the process at a much higher level. The line manager, for example, is going to just be looking at the information coming out of the systems. It doesn't matter how, it doesn't matter to them how that comes out of the systems. That's what the data fusion is about. And so that does allow for portability, both from the workers and then also getting that data and integrating it into the company's overall system. So they might, there might be a company with 20 lines distributed across the US, right? And so the idea is if they're on the same data fusion system, then they can have information from all of those locations available to management and the line managers, and they can switch around, but the information is the same because it doesn't matter what setup you have or what country you're in. If your solder paste is too dry, then the information your solder paste is too dry is portable.
Perfect. Matt has a question for you, JJ. He's asking, once these initiatives are put in place and the strategies are executed, will it matter where factories are located? In other words, we'll have to pay the right rents in San Diego or Fremont if you can plop the same factory in very low real estate locations like middle of Nevada or Montana?
Well, I mean, no. So you won't need to worry about location as much as you do about the process, because it's really going to come down to the actual process. What this is going to allow is taking a known system of whatever location and whatever individual components you want, as long as you can understand the system and you know how to optimize it and you know how to control it and you know how to report it. It doesn't matter who's operating it and where it's operated. This is one of the benefits.
Great. So that's all the time we have for today. Thanks so much, JJ, for hosting this fireside chat with the experts. And please tune in. We have another very interesting chat next week with, it's going to be hosted by Griffin Lemaster about robotics and how we use it for automation of processes, specifically X-ray inspection. Thanks so much for watching. Until next time. Thank you.
Quay, what you want?